Welcome back, everybody. This is the beginning of our Chapter 4 notes on two-dimensional kinematics, also known as projectile motion. Now, you may remember that kinematics involved the movement of objects in a straight line. It could either be in a horizontal line or vertically. Vertically, we call that free fall, of course, but horizontally, you could have something accelerating an object, creating an acceleration, and changes in velocity and therefore changes in position. But two-dimensional kinematics is going to be the study of kinematics in two directions at the same time. And as we do some examples, I think that'll become more evident how that works out. But kind of a more commonplace name for it is just projectile motion. And a projectile is really anything, any object that is launched into the air. So it's given some sort of initial velocity. And then it follows a path that is basically guided by the influence of gravity. As the old saying goes, everything that goes up must come down. That's certainly true with projectile motion, but with our understandings of kinematics, we should be able to predict where it's actually going to come back down. A couple of assumptions, though, that we're going to make, and these are actually going to make our lives a little bit easier. Air resistance is 0. All right. We will measure types of resistance later on in the year, and they would be measured in things called newtons. Newtons is a measure of force, and air resistance can create a level of force, certainly in the real world, but we're going to pretend that it doesn't exist. All right, we're not going to be able to account for that in this class. We're going to study projectile motion as it were in a vacuum, without the effects of air resistance. Okay. Another assumption is that the acceleration of gravity is constant. We've kind of assumed that all along, especially in our free fall chapter, and we've been assuming that it's 9.8 meters per second squared is the acceleration of g in the negative direction. But in truth, it's not really always the case. Sometimes, let's say if you're on top of a high mountain, you're further from Earth's center, and therefore there's going to be less gravity. Also, if you're down closer to sea level or at a very, very low elevation below sea level, you can experience more gravity. So gravity does fluctuate, but our assumption is that it's going to remain constant, and this is going to be our value that we've been using all along. And we're going to ignore the Earth's rotation. There's a funny sort of phenomenon called the Coriolis effect, that when objects move in a straight line over a rotating Earth, they tend to move in not so straight lines, but curved lines. So let's say we have our Earth right here. All right, and not a very well drawn Earth, but that's a little bit better. And let's say we have our North Pole here right at the top. Okay, and our South Pole down here. And it's rotating, as it always does, towards the east, like that. Okay, if you have a projectile, like let's say a worldwide projectile, let's say, I don't know, like a missile that could go from continent to continent, we would call that an intercontinental missile. If it was going to try to move in a straight line, all right, so here's our missile right there, trying to move in a straight line. Well, it moves over a rotating Earth, it's actually going to bend off to one side or the other. There's a couple of reasons for this phenomenon. We're not going to get into it, but in real life, that's what happens. We're going to pretend that it doesn't. All right, so we're going to ignore the Earth's rotation. Some people have actually even blamed the Coriolis effect, or this rotation of the Earth, for golf balls to have been hooked or sliced one way or the other, or otherwise home run balls in baseball to be fair or foul. Not sure that's certain that's necessarily the case on such a small scale, but on a large scale, like over global distances, it definitely is. But we're going to pretend that it doesn't exist. Okay? So, those things being said, let's look at some things that are a little more familiar. These equations right here are our big three equations for kinematics. We actually had 5 total, but we use these 3 the most. Now this first one right here, position as a function of time. This one right here should look very, very familiar to you. Now we had a kind of a modified version of it. Instead of y, really this should say y final. I'm going to use a better color than orange. Y final equals y initial plus vi yt minus 1/2 gt squared. instead of having the final and the initial on different sides of the equation, we had the initial over here, and it was simply final minus initial, or delta y, right? Or in this case, if we brought the x initial over, it was delta x. But those equations should look familiar. All right. Similarly, down here, v final of x, v final equals v initial minus acceleration times time. V final squared equals v initial squared minus 2 times acceleration times the displacement. So these are all still very much in effect. But you'll notice that these are kind of truncated a little bit or slightly shortened in some cases. So I'm going to erase my wonderful doodles right here and just kind of clarify what really is going on. Sorry, give me a second right here. Okay, the assumption here, another assumption, is that the acceleration in the x direction is going to equal 0. That's our big assumption. I kind of shifted the thing around here a little bit. There we go. What that means is that anything in the x direction with an x component is going to have zero acceleration. So anything with acceleration in it is going to get dropped off. Let's see here. So this right here used to say x final equals x initial plus v initial x times time plus 1/2 acceleration in the x times time squared. But since there's no acceleration in the x direction, that whole part gets dropped off. All right. Now, we certainly know there is an acceleration in the y direction. What do we call that? We call that gravity. That's why we got our g right there. So our y final position equals y initial plus v initial times v initial of y times time minus 1/2 g, which is certainly an acceleration in the y direction, times time squared. So these are our working equations for position as a function of time. So if you want to find out the final position of an object after a certain amount of time has elapsed, these are the equations that we're going to use. And so we have these two different versions of these equations right here because we have two conditions going on in the x direction and the y direction. In the x direction, there's no acceleration. There's no acceleration because nothing is making it move faster or slower in the x direction. Let's say an object is shot out of a cannon. Yes, it's given an initial x velocity, but nothing's making it move faster or slower. It doesn't have a rocket on it. It's a projectile. It doesn't have any kind of jets or self-propulsion. It is simply moving through air at the velocity that it was originally given in the x direction. But it is true that there's an acceleration in the y direction. In the y direction, it's going to slow down as it goes up, and then it's going to stop and then start accelerating downwards due to that negative gravity right there. So that's why with the y directions, we have the gravity included right here, because gravity is certainly going to bend the trajectory of these things back down to Earth. Same thing with velocity versus time, our equation right here. Well, since there's no acceleration, then the initial velocity is going to equal the final velocity in the x direction. In the x direction, that's key right there. All right, see how it has the x subscripts right there. So the final velocity at any point, v final x, is going to be the initial because there's no acceleration. However, there is certainly going to be a different initial or final velocity in the y direction versus the initial velocity in the y direction because there's this change of velocity in the y direction that we call gravity. Lastly, we have an equation that gives you a velocity as a function of a certain height, of a height y, all right, our delta y right here. Well, once again, if an object is moving up and over, it has an x component and a y component, it's not going to have any x acceleration because once it's given its x component of velocity, it's going to maintain that, and we're going to assume that nothing's going to slow it down. There's no change in velocity, there's no acceleration in the x direction. There is, however, as we know, that change in velocity in the y direction that we call gravity. So that's why we're going to have this. This is the full equation that we've been using. This is a shortened or truncated version of it because there is no acceleration in the x direction. Okay, so these are going to be the equations that are going to be really important to us to determine where an object is or how fast it is going at a certain point in time or at a certain height. All right. One thing I should point out is that since even though I kind of highlighted these both in red right here, these are both the same equation, but the motion in the x direction and the motion in the y direction are completely independent of each other. Same here. X and a y direction completely independent. There's some sort of x motion and some sort of y motion, but since x and y axes are at right angles to each other, there is no the one you might say the one component, the one axis does not affect the other in the least. So they're completely independent of each other. The one thing that ties them together, however, the one thing that they have in common is time. If an object moves, so let's say we have, I'm just going to do a quick little scribble right here. All right, an object is shot out of a cannon on the ground, so a cannonball. So it moves over some x component, and usually I write x's in green. Okay, sorry, change in x position, and it moves up in some y value from there to there, right, our delta y. We've got a completely different change in position in the x as in the y. We've got a completely different change in velocity in the x as in the y, different accelerations, different initial, everything. But the one thing that is the same, from here to here in the x and the y direction, is the amount of time that is elapsed. Time in the x direction equals time in the y direction as it moves from the initial point to any other point. And that's going to be a really big player in our equations moving forward in our applications. All right. So in the next video, we're going to be doing some examples of projectile motion, and we're going to start with what's called zero launch angle. Now, the little drawing that I just did showed a cannon kind of aiming up into the air. Well, to start out, we're going to aim our cannon, as it were, at a 0 degree angle, completely horizontal, and shoot our cannonball out like that. Okay, so remember how we measure angles based from the horizontal. All right, and if the initial velocity, or the initial direction of motion, initial velocity is completely horizontal, and then there is a 0 angle. That theta is 0 between that and the horizontal. All right, so initial velocity in the x direction. All right, now so this is the initial velocity overall, but I'm going to write initial velocity in the x direction in green, as I tend to write x's in green. So initial velocity in the x direction. Well, what's the x component of something? Well, it's going to be, as we found out in vectors, right? It's going to be the full magnitude of whatever is, whatever the measurement is, initial velocity, times the cosine of theta, right? And in this case, the theta is 0 degrees. There's a 0 degree launch angle right there. So if you ever key in the cosine of 0, what does that give you? That gives you 1. So that means the full value of the velocity of this thing coming out of the cannon is going to be in the x direction. Okay? It's moving completely in the x direction. There is no y component, and we can actually prove that because if we have that same angle, 0 right there, what's the initial velocity in the y direction? Well, that's the initial velocity, that is the vector value, times times the sine of that angle theta. Well, if that angle is 0, the sine of 0 is 0. So there is no y motion here. all the initial motion, all the initial velocity, this red one right here, is directed in the x direction. However, we're going to see a little bit later that that's going to change as we do our first examples. All right, especially with regards to zero launch angle. Okay, so real quick before we jump into our examples in the next video, just to recap, this is our position as a function of time for the x and in the y direction. Y has an acceleration, x doesn't. This is velocity as a function of time, and you can see that since there's no acceleration in the x direction, final velocity at any point is going to be the same as the initial velocity in the x direction, so it's constant. The final velocity in the y direction is going to change because of that acceleration of gravity in the vertical. And this is velocity as a function of displacement. All right, and once again, initial velocity in the x and final velocity of the x are going to be constant because there's no acceleration in the x direction. Not true in the y because once again, we have that vertical acceleration that we call gravity. So that's going to be it for now. Thanks for following along. I'll see you in the next section when we start some examples.